Hello, everyone. I am Heng Chen, coming from Tsinghua University. This presentation shows our work accepted by BMVC, named Dense Contrastive Loss for Instance Segmentation. You can contact me via the email address below if interested in this work. In this work, we aim at instance segmentation, which is a fundamental task in computer vision. Instance segmentation requires instance-level mask prediction, which is a more fine-grained task compared with object detection and semantic segmentation. Despite many methods have been proposed, they still do not perform well in complex scenarios, such as occlusion and low illumination. We start with analyzing the errors in the instance segmentation. Here we ask two questions. Which type of error is the dominant one? How to diagnose the errors in instance segmentation? For the latter, AP metrics are too coarse to draw fine-grained conclusions. Some existing error analysis tools, such as TIDE, are designed for detection and cannot be used to analyze segmentation errors. Thus, a systematic analysis is desired before proposing better methods. We classify the instance segmentation errors into detection and segmentation errors, providing a fine-grained analysis of the segmentation errors. As shown in the figure, segmentation errors are decoupled into three types. The foreground false positive errors indicate that the model is confusing different foreground instances. Background false positive error means that the model incorrectly treats background pixels as part of the foreground. The false negative error refers to that the model incorrectly treats foreground pixels as background. That is, predict incomplete masks. We then quantitatively analyze each error, correcting its corresponding error pixels for a specific error type, denoted as O, improves the segmentation results from AP to APO. The AP gap indicates the severity of that error type. We found that false negatives accounted for the majority of segmentation errors. In other words, the model tends to predict incomplete masks. We attributed this to the fact that in complex scenes, segmentation networks cannot predict consistent features for different pixels on the same instance. With this motivation, we propose to improve the consistency of features via contrastive learning. We take mask RCNN as an example to introduce our method. We randomly select anchor and positive samples from the target instance. The negative samples are selected from the rest of the ROI. By applying the inference loss, features on the same instance are pulled closer, while features on different instances and features between instances and the background are pushed farther apart. For the one-stage model, we make the following small modifications. First, replace ROIs with ground truth bounding boxes. Then, get ROI features by Royalin. Finally, apply the dense contrastive loss to ROI features. We found our method effective in alleviating false negative errors. Meanwhile, our method leads to a more consistent feature of the pixels on the same instance. The t-SNE visualization of the ROI features shows that the features learned with our method are more compact. We compared the proposed method with the previous methods on the Cityscapes dataset in the table. Our method achieved consistent improvement on different baseline models, improving the test set AP by 1.6% on the powerful RefineMask baseline. Note that our method does not introduce any test time overhead, and therefore does not affect the efficiency. We also report the results on SparseInst, which is a recent state-of-the-art real-time method, and mask RCNN with a larger backbone. The experiments were conducted on the COCO dataset. For SparseInst, we applied DCL to the output features of the mask branch. Our method achieves consistent improvement on these recent and stronger baselines. We present some qualitative results on the Cityscapes validation set. Compared to the mask RCNN baseline, our method yielded higher quality and more complete masks. Our method also produced better results for the extremely crowded cases. We hope our work will improve the understanding of errors in instance segmentation and advance the study of contrastive learning for downstream tasks, such as instance segmentation. That's all. Thanks for your attention.